All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. Glad you can join me. It seems like almost everyone is here, but we'll go ahead and get started. Let me share my screen. There we go. And let me make sure that I can see the chat and everything. Bum, bum, bum. A couple more people trickling in. Let's let them in. All right. Okay. So I will begin by saying something about oh, my phone was making noise. Okay. So traditionally, I mean, you guys could have your video off, and that is still allowed if you want. But now Zoom has this new feature where I can actually spotlight my video. So during the recordings, only my video would get recorded. And so I think it'll be nice if I could see you guys, if you find yourself presentable or something like that, that would be nice. But of course you don't have to. But just to make things look a little bit more personable would be nice. So that being said, let's actually continue. So we have an exciting lecture today, at least I think. It's on the Weierstrass substitution. I'm pretty excited for this because it's one of those things that I guess in a typical Calc 2 course, they don't teach this technique, but it's one of those techniques that I wish I had learned in Calc 2, much like the tabular method. Like I learned the tabular method long after I did Calc 2. I'm like, why did no one tell me about this? I've been doing integration by parts with all these nested parentheses forever. Like no one told me about this. So the Weierstrass substitution is another one. And it's not that crazy, as we will see. So I'm going to teach you a different kind of substitution. And basically, it's kind of going to be like a reverse trig substitution. So remember we had the trig substitution where we had a certain kind of expressions. We saw things that looked like x minus a squared minus x squared, or x squared plus a squared. And there were no trig functions around, but those sum of squares or difference of squares reminded us of some trig identities. And so we inputted trig functions, hopefully to get something easier. The Weierstrass substitution is literally in the reverse order, meaning we have an integral that has trig functions there, and we actually want to remove them. And we can remove them by technically introducing inverse trig functions and to get rid of the trig functions. And the hope is the integrand without the trig functions would actually be easier. So sometimes it's actually the other way around. So it's kind of like a reverse trig substitution. It's also called the inverse tangent substitution, because it turns out that the inverse trig function that you introduce is always going to be an inverse tangent. So you'll never have to worry about, oh, should I use an inverse sine or an inverse cosine? And I think, for certain exotic integrals, those guys might work. But the inverse tangent is actually pretty useful substitution and can handle a wide array of situations. So that's what the Weierstrass substitution is about. So I'm going to tell you what that substitution is. I'm going to derive how you would actually make changes to your integral based on this substitution. After that, though, things are pretty much going to revert to old techniques that we've had. So after I've applied the Weierstrass substitution, I'll get input from you guys on how to proceed. That being said, let's actually just go in. So first of all, what kind of integrals can we use this substitution for? Well, it can be pretty general, but it's mostly useful for rational trig functions. What is a rational trig function? Well, it's kind of like if you had a rational function, but instead of the variables, you have trig functions. So for example, that's comparing something like 1 over x plus y plus 1 versus 1 over sine x plus cosine x plus 1, right? So instead of this polynomial, we have something that kind of looks like a polynomial, but instead of the variables, there are trig functions. Right? So this is called a rational trig function, at least that's how I'll term it. So it turns out very often, or I shouldn't say very often, sometimes we can actually simplify an integrand that looks like a rational trig function by introducing this particular kind of substitution. We will set a variable t equals tangent of x over 2. And it's always going to be that, right? It's always going to be a tangent. So you never have to worry about any other trig function. Always t equals tangent x over 2. where x is the original variable, right? So if it's thetas, it's t equals tangent of theta over 2, right? Now, once you apply this substitution, you treat it like any other substitution. You have to find the dx and all that stuff and how to switch everyone over. So that is where our lesson begins, right? So if I have some integral of f of x dx and it's a rational trig function and I make this substitution, what happens to the dx, right? Well, that's a reasonable question. We should always know that. So let's actually figure that out. So if our t is equal to tangent x over 2, this means, of course, I could solve for x, and this would be 2 tan inverse of t. And then what I can do is I can actually just differentiate both sides. My dx would be, well, 2 over 1 plus t squared dt, right? Because the derivative of tangent inverse is 1 over 1 plus t squared, and the 2 was there before. So that's what would happen to my dx. So that is what dx becomes. So once you apply this substitution, you just replace your dx with 2 over 1 plus t squared. And that's just something that you will know how to do, right? Now, what happens to the other trig functions that appear, right? So what are the trig functions? Sine, cosine, tangent, secant, cosecant, cotangent, right? If we know how to deal with sine and cosine, we know how to deal with everybody, right? So to get, if I tell you what the sine and the cosine are, you can figure out the tangent by dividing these two. Divide them in the opposite order, you get the cotangent. 1 over the cosine will give you the secant, 1 over the sine will give you the cosecant, etc. So let's actually figure out what happens to sine and cosine under this substitution. So if our t is equal to tangent x over 2, what that means is I can create a triangle where the angle is x over 2. And t, I can think of that as t over 1. And so we here have opposite over adjacent. Pythagoras' theorem will tell us that this is 1 plus t squared square rooted. And now we can actually talk about the sine and cosine based on this triangle. So this would mean that, say, the sine of x over 2 and that's going to be opposite over hypotenuse. And the cosine of x over 2 is going to be the adjacent over hypotenuse. I'm writing at a slightly different scale here. The thickness of the pen is kind of like weirding me out. Okay, so now we have those. This means that if I have a sine of x, I can think of this as a sine of 2x over 2 and apply the double angle formula for sine, which is going to be 2 sine x over 2 cosine x over 2. So if I multiply the sine of x over 2 by the cosine of x over 2 and multiply that by 2, I would get 2t over 1 plus t squared, which means whenever I see a sine x in my original function, I can replace it by this expression. Similarly, if I see a cosine of x in my function, I can think of this as a double angle. And so by the double angle formula, that means that's cosine squared x over 2 minus sine squared x over 2. And from above, that means I'm going to square this guy and then subtract the square of that guy. So that's going to give us 1 minus t squared over 1 plus t squared. And that's my cosine of x. Okay, so with this substitution, I can make this substitution, t equals tangent of x over 2. My dx is going to become that. Everywhere I see a sine x, it will become that. Everywhere I see a cosine x will become that. And of course, once I have the sine and cosine, I can figure everyone else out. So this leads us to, here is the summary. And those are the examples. So ultimately we get to this. And I thought I had a box around this before, but maybe not. So I'm going to draw a box around this. So this is what you want to remember from this technique. Right, so you can actually take a screenshot of this because we're going to be using it. So if we have an integral of f of x dx where f of x is a rational trig function, the Weierstrass substitution is t equals tangent of x over 2. It's always that, right? It's always going to be t equals tangent x over 2. Okay, and with this substitution, your dx is going to become 2 over 1 plus t squared dt. Your sine x is going to become 2t over 1 plus t squared. Your cosine x is going to become 1 minus t squared over 1 plus t squared. Your tangent x would, of course, be, if you divide these two, 2t over 1 minus t squared. And your cosecant, secant, and cotangent becomes, you know, the reciprocals of the previous three based on prior trig functions, right? So that's basically all you need to know about the Weierstrass substitution. Once you actually apply this, everything else is using previous techniques. It's okay, Chloe. Everything else is using previous techniques. And then you would ultimately be able to solve this integral of t, hopefully easier than the original function that you had. And then you would just replace the t with tan of x over 2. So let's actually see this in with some examples. So we have some examples here that I'm going to go over, including example F. Pretty excited about that. I told you guys how to integrate secant x in the beginning of the course, where we just out of the blue multiplied by this random thing. And it was like, why would we know to multiply by that? So it turns out the Weierstrass substitution provides a direct computational way for this. You don't have to figure out some phantom thing to multiply and divide by. We can actually directly compute this guy, and we'll do that pretty soon. But we're going to do all of these guys. Now, the first one, you can actually do it in several different ways. So I'm actually going to ask you two ways to do that. First way is we're going to use the Weierstrass substitution so you can see what it would look like. But then I'm going to ask you guys to do it another way. So let me move this out of the way right here. So let me run through the Weierstrass substitution for this problem. Okay. So I see this. Here's an integral 1 over 1 plus sine x dx. I would like to compute this integral. Let's say for some reason I don't know how to actually tackle this. Technically, with what I've told you before, we would know how to tackle this integral. I also believe I put a very similar integral in a quiz before, but I digress. Let's say I didn't remember I could multiply and divide by something mysterious to make everything work out. But this is a rational trig function, so I'm thinking, let's try Weierstrass. So this means you set t equals tangent of x over 2. This means that your dx is going to become 2 over 1 plus t squared dt. The sine of x is going to become 2t over 1 plus t squared, right? From the previous things. So you guys can look at what we had up here. And so now when I go and I plug into this integral, this is the integral of 1 over 1 plus, the sine is 2t over 1 plus t squared. And my dx becomes 2 over 1 plus t squared dt. So now this is just a regular integral. We're going to use previous techniques. But first, let's actually simplify. Let's multiply this across, the 2 times that. This multiply that, multiply that. So here I will have 2 on top. On the bottom, I would have 1 plus t squared by multiplying the 1 plus t squared times the 1. If I multiply the 1 plus t squared times the 2t over 1 plus t squared, the 1 plus t squareds cancel. So I'm just left with 2t. So now this becomes the integral of 2 over t squared plus 2t plus 1. And this just becomes what? Well, how would you integrate that one?
Would you do like t plus 1 squared? And you could do partial fractions.
Come again?
You could do t plus 1 squared and then do partial fractions.
So you'd want to factor this, t plus 1 squared. Would we need partial fractions for that?
No.
No. How would we do it?
Would you do a u substitution of t plus 1?
Right, and your du would be dt, so it will behave like 2 over u squared. You integrate 2 over u squared, you get minus 2 over u. So this just becomes minus 2 over t plus 1. And so this would be now, you go back, you plug in your t. So this is minus 2 over, our t was tan x over 2 plus 1. And that is our integral. Okay, so of course the Weierstrass substitution, the new concepts that we learned, all happen in the beginning. It's literally, it shows us what we need to substitute to change the integral from a rational trig function to just a regular rational function. Once you're in with the regular rational function, now you just apply old techniques. Maybe you'll need a partial fractions. Maybe you'll need a substitution. There's no telling what you're going to end up with, but the hope is once you end up with something, you'll know how to tackle it. Okay, so that's an answer. That is the antiderivative, and you can actually take the derivative of that, and you will get back 1 over 1 plus sine x. Another way. Prior to today's class, how would you have tackled this had you seen it? Pretty sure I put a problem like this on a quiz, but it was a few quizzes ago, so I don't remember. Ideas on how you would tackle this? I never knew about the Weierstrass substitution.
Can't you multiply by 1 minus sine x over 1 minus sine x?
Right. Right, so here you'd realize without the Weierstrass substitution, you'd have to kind of see that there's this convenient thing that you can multiply and divide by in order to simplify things a little bit. Why? Because now the denominator becomes the difference of squares. And of course, 1 minus sine squared is cosine squared. How would you integrate that?
First, I would separate it into 2 different fractions.
Right. So the first one is going to be a secant squared, and the second one is going to be sine x over cosine squared. Integral of the first one, we know that, right? Integral of secant squared is just tangent. Integral of the second one, how would you do the integral of the second?
Couldn't you take out a sine x over cosine x, replace that with tan x, and then what you have left would be 1 over cosine of x, which is secant of x.
Mm-hmm.
So sine x over cosine squared of x is actually secant x tan x.
Okay, and the integral of that?
That's secant of x, right?
That's just secant of x. Another way you could have done this is with a substitution. Also, you could do something like u equals cosine. For du would be minus sine. And so this would just be the integral of minus 1 over u squared. That would be the integral of minus 1 over u. And then that would be just minus 1 over cosine, which is just minus secant. And then the minus makes it right. And then you get that. Yeah. And then you put that here. So a couple ways you could do that. But you can get the answer another way, right? Now, of course, this looks different from our answer, but I can promise you whenever you can plug in an x value into both of these, they will ultimately give you the same function, the same antiderivative. To differentiate each of these, they might differ by a constant, but chances are you can simplify one into the other. But yeah, that's that. Okay, so the Weierstrass substitution, we could do it here. If you're in a situation where you can't really figure out, what would I multiply or divide by, right? Like out of the blue, some random, how am I gonna come up with some random convenient thing, right? Versus this is like a direct, straightforward way. Like if I have a rational trig function, this is something I can do where I don't need to think about something that I can't even see. So, but for this example, it wasn't the only game in town. However, look at this example here. It turns out that this example isn't as nice as the previous example, right? Because what would you try to do here? Right? Like if you were to multiply and divide by something convenient, you'd probably think, okay, I can multiply and divide by 3 plus 2 sine x. Now the denominator would become 9 minus 4 sine squared. What do you do with that, right? You'll go down a hole, and you can try this out for yourself at home. You are at home. And you'll kind of see that the previous technique, the last technique that we used for here, kind of trying to multiply and divide by something convenient, it's not going to work out so hot for you, right? Because of the fact that the 3 and the 2 are different numbers. We got away with that here because the coefficient of the sine and the constant were the same. When things are different, it's a little bit trickier. However, the Weierstrass doesn't care. Weierstrass is like the honey badger. So here you can just actually jump straight in by Weierstrass. You know that your dx is going to become 2 over 1 plus t squared. You know that your sine of x is going to become 2t over 1 plus t squared. Let me just rewrite the Weierstrass here so you don't forget it. And so now the integral will become 1 over 3 minus 4t over 1 plus t squared times dx, which is 2 over 1 plus t squared. And as always, I'm going to take this, multiply the denominators. So this would be 2 over, this is 1 plus t squared minus times 3. Minus 4t. So here we can simplify this to 3t squared minus 4t plus 3. Okay, so by applying the Weierstrass substitution, I have this very weird rational trig function that I want to integrate, but then I can simplify it into this rational function. What do we do now? So at this point, we can use previous techniques, which you guys are hopefully all experts on by now. See this integral, what do we do?
factor it?
Does it factor? Or right, does it factor would be one of the first things I would ask myself. Right? So that would probably be the first thing I would ask myself. Does the denominator factor? It's probably one of the first things I would ask myself, because then I would think about maybe doing like a partial fractions, because there's nothing in the numerator that would make a substitution work out. So I would think, does it factor? Does it? I mean, there's only kind of one option here with the first coefficient. It has to be a 3t and a t. Can I actually get that to work out?
3t minus 3 times t minus 1.
No, because that would make a middle term -6. Also, by choosing the 3 in the first set of parentheses, that means that I could factor out a common 3, but I couldn't do that in the beginning. So if the 3 and the 1 were to be placed here, the 3 would have to go here and the 1 would have to go there. In which case, that would give me 9t. This would give me 1t. Can't make a -4 out of a 9 and a 1. So doesn't factor. Okay, so now that we know that it does not factor, what do you think?
Complete the square.
Complete the square, right? So if it doesn't factor, this means complete the square. Okay, but you'd kind of want to think in that order. So you see some rational function. Of course, the first thing you're going to think is it a basic rule? Can I simplify it to be a basic rule? Would a substitution work? None of those kind of pan out here. So the next thing you try to see, well, okay, it's a rational function. Maybe partial fractions would work. For that to work, I need to be able to factor the denominator. So that's the first thing I would think about, factor the denominator. Then if it doesn't factor, now you start to think maybe I complete a square or something like that. So what would that look like here? So this would be 3. So here, I would have to add half the coefficient of x and square it. So I would add like a 4/9 minus a 4/9. The first 3 parts are going to become a complete square. That's going to be t minus 2/3 squared. And I'd be left over with the minus 4/9.
Professor?
Yes.
Would that be 4/6 if you're doing half of 4/3?
Yes, but 4/6 is the same as 2/3, right? Like half, I would just take half of the numerator. 4/6 simplifies to 2/3. 2/3 squared is 4/9.
Okay, thank
Yeah?
you. Yeah.
Yeah, and so now this would come down to 3 times t minus 2/3 squared minus 4/3 by multiplying out that 3 plus 3. 3 is the same as, I want to write this as over 3. So that's 9/3, right? So that's 9/3 minus 4/3. It's 5/3.
What's plus 5/3?
Plus, yes. Okay. Okay, so now there are a couple ways to deal with this one, right? And this is going to be something that's going to come up. I think I have some examples later on where this is going to come up. But at this point, you might be thinking, oh man, now I'm going to have to hit it with a trig sub. However, there is a nice formula that we know that this kind of reminds us of, or should remind you. Right? We have 1 over a variable squared plus 1. Or with a little less calculation, you can remember this one. Right, so these are two forms that I highly recommend worth memorizing. I did put it in the table of basic rules that you should know. Either one you can memorize would be nice. I guess the second one would be a little bit nicer than the first one. The second one does include the first one for setting a equals 1. But yeah, so we can actually get this to work out a little bit nicer here. So with that in mind, all I need to do is finagle this one to sort of look like that one, right? And what I can do with that is something like the following. I can write the 3 as, say, a radical 3, but square it. And say do something like a u equals radical 3 t minus 2/3. My du would be radical 3 dt. And so 1 over radical 3 du would be dt. And so this integral is going to become 2 over radical 3 times the integral of 1 over u squared plus 5/3. And now my 5/3 just means my a equals radical 5 over 3 in this formula.
Professor,
Yeah.
would it have been easier in the beginning to factor out the 2/3 before?
What part?
So the step where you have the blue should remind you of.
Factoring out the 2/3, no. Maybe factoring out the 3.
Okay.
Yeah, but factoring out the 2/3, not really. You can't really factor out the 2/3 because it's not a common factor, right? It's the t minus 2/3.
Okay. I meant like the 2/3 from the numerator and the denominator.
Yeah, you could do that, and you'd end up with 2/3 in front, and you'd end up with a 5 over 9 as the constant. Yeah.
Thank you.
Ultimately, you'll end up with the same thing, ultimately. So it doesn't actually really matter here. Like once you simplify everything and they'll both simplify to the same. So yes, that would be okay. So at this point, it becomes 1 over a. So this just becomes radical 3 over radical 5 times tan inverse of u over a. So it would become radical 5u u over a, radical 3u over radical 5 plus c. And so this would become 2 over radical 5 tan inverse of radical 3 over radical 5 times our u was radical 3 times t minus 2/3. Which, plus c, which simplifies into the radical 3 times the radical 3 gives you 3 over rad 5 t minus 2/3. And you'll notice that had we done what you suggested earlier, where we got the 5 over 9, then that would mean your a would be radical 5 over 3. and then the 1 over a would become the 3 over radical 5, right? So that's where you see it there. And what you have left over in the front, the constants would have canceled out, and you would have that. So that one was a long one. But it would actually have been longer had we tried to do that thing where we multiplied and divide by 3 plus 2 sine x and try to squeeze out some random trig function identity out of it. So here, we didn't have to worry about multiplying or dividing by anything. We hit it with Weierstrass. The dx turns into that. The sine x turns into that. Ultimately, I get to this rational function. At this point, we're in previous material territory. Now you just go through the Rolodex. Okay, is it a basic rule? Can it simplify to be a basic rule? Can a substitution work? None of that works. Then I realize, oh, it's a rational function, it's a ratio of polynomials, maybe a partial fractions, please be partial fractions. Then you say, the denominator has to factor, it doesn't factor. So now what you do is you complete the square instead. Now, under a lot of circumstances, you would need to do a trig sub after that. However, because you have this nice little formula of a variable squared plus a constant squared, you can kind of use that to your advantage. Just get the denominator to look like a variable squared plus a constant squared, and I can do a substitution to get that done. And so I'm left with that. So not a trivial example. However, with a lot of practice, with going through each of the techniques individually and doing a lot of homework on each of them, you'll see how to mix and match them to get what you need to get done. And a part of, I don't know if I'll get to it, but maybe this will spill over into Monday. A part of what I'm going to do, like I said, this is the last integration technique I'm going to teach you. So the next phase, the next thing I'm going to teach you is how to recognize when to do what. Here I'm mixing a bunch of techniques. How would you know to mix these particular techniques in this order? How would you know to have approached it, right? So we'll actually deal with that, so don't worry. If you can understand what happened here, like in general, I think you're in good shape at this point. If you are worried about, yeah, I see what happened, but I would never have known to do that myself, don't worry, I have you covered, we will deal with it. For now, I'm just showing you how this technique would actually work. When it comes to actually mixing and matching techniques and when to use which technique, that's something that we will deal with separately. But hopefully, otherwise, everything was clear in terms of a play-by-play of what we were doing. Unless, are there any questions about what happened in this example? As I was going through it or before? Okay. Here's another one. Sine x over 1 over sine x plus tangent x. Okay, so by Weierstrass. Someone got kicked out of the room. Let them back in. Okay. All right, now it's your time to practice. Hit it with Weierstrass, what happens? I write very lean on this thing. Well, we're going to have to change the dx. We're going to have to change the sine x. We're going to have to change the tangent x. What is dx?
0 over 1 plus t squared.
dt. Okay, what is the sine x?
Qt over 1 plus t squared.
Mm-hmm. Tangent x?
Qt over 1 minus t squared.
Okay. And now we're just going to plug these guys in. So it's 1 over sine plus the tangent. So it's 1 over the sine, 2t, over 1 plus t squared, plus the tangent, times 2 over 1 plus t squared dt. This would simplify into 2 over, multiplying out the 1 plus t squared, I would get 2t, plus here I would get 2t times 1 plus t squared over 1 minus t squared dt. How would we deal with this integral here?
I'm not sure if this would do much, but you could factor out a 2t in the denominator.
Okay.
So you get 2 over 1 plus 1
Yeah,
over...
but we have like a fraction in the denominator, right? So that would make me uncomfortable. I don't know if it's making anyone else uncomfortable. The fact that I have a fraction in a fraction. I mean, the 2's I can cancel at any point, sure. So like I can cancel this out. But what about the fact that I have a fraction in the denominator? How do I
Can we
fix that?
combine the fractions into 2 and then put the denominator up on top?
Right, but nicer would be to multiply by the LCD. So that was a trick that you had. Multiply and divide by the LCD. That will clear all the fractions and like combine all the fractions all in one swoop. So the numerator would become 1 minus t squared. The denominator, I would have t times 1 minus t squared plus t times 1 plus t squared. Right? So that's like combining fraction denominator, keep, change, flip to simplify. You can do all this in one step by multiplying and dividing by the LCD. So now we're here. So now at this point, what I would do is multiply these guys out. So this is t minus t cubed plus t cubed. Of course, the t cubes cancel each other. Oh, lucky us. And so this is 1 minus t squared over 2t. That all simplifies to that. How would I integrate that?
Substitution.
Substitution.
Actually, no, never mind.
No.
We
That's
split
what
it
we
into
would
2
do.
integrals.
Split it into 2, right? Start back at the beginning, right? Is it a basic rule? Can it simplify? You can simplify this. You can split it into 2 parts. 1 over 2t dt minus, well, t over 2 dt. Each of these is a basic rule. So this is 1/2 ln of t minus this guy here is going to be t squared over 4. And what is my t? What it always is in Weierstrass? Tangent of x over 2. With these, as you can probably tell, one of the most challenging parts is algebra. So it's just like simplify this fraction so we can actually do something with it. Yeah. So yeah, you ever wonder what your teacher is talking about multiply and divide by the LCD in algebra class? Why do you need to know this? Why am I ever going to need to? Yeah. Turns out for a while it's going to be true that a lot of the math you're learning is just to do other math. Like you learn math for the sake of being able to do higher level math. Like you need the basics. The higher up you go, you still need the basics. It's going to be a while before you can actually apply the math directly because the world is too complicated right now.
Professor?
Yeah. Yes.
I have a question. When you scroll up, when you do the first canceling out of the fraction on the bottom, like when you first multiply by 2 over 1 plus t squared,
Yes.
couldn't you also, because that still leaves you with the other fraction of 1 minus t squared, couldn't you, in that first step, multiply by 2 over 1 plus t squared times 1 minus t squared?
Right, but you'd still have to multiply by the 1 minus t squared at the same time.
Yeah, that's why I'm saying, like, in the
Yeah,
denominator.
you could have, in the very beginning, multiply by 2 times 1 minus t squared over 1 plus t squared times 1 minus t squared. Yes, you could have done that in the beginning. But that would just be using this step up here. And getting everything done at once, because you realize that the denominator on this part here is already different. So you could just decide to clear it all at once by multiplying by that at that point. So yes, that was an option.
In the final
But
integral,
I didn't want to
should
do too many things at once though. But yeah. Who else was talking?
I was sorry.
Yeah.
In the final integral, should there be a 2 in your absolute value of ln of absolute value?
Where should the 2 be?
Because you did a u sub with u is 2t, so du is 2 dt.
Well, I didn't do that, but even if I did, what I did was if I had the 1 over 2t,
Oh, that makes sense.
I factored out the half.
Got it.
But even if I did do the u equals 1 over 2t, if I did u equals 2t, then my du would be 2 dt. So I'd have 1/2 du is equal to dt. And so I would have 1/2 times the integral of 1 over u du. And then I would get 1/2 ln of u, absolute value. This would be 1/2 ln of 2t. This would be the same as 1/2 ln of 2 plus 1/2 ln of t. And this part here, I would just move into the constant and I would end up with the same thing.
Okay.
Yeah, but I wouldn't have substituted u equals 2t. I'd just factor out the half. Like when I was thinking about it, I just thought about it as factoring out the half. To clean it up would have been too cumbersome, because then you'd have to realize I could split the ln and then move part into the constant. So chances are, if you were to look at this in the back of a textbook that used Weierstrass, they would write the answer like this, and you're like, why doesn't there ln of a 2 on it, and where's this other part? Yeah. So, okay. So that is that example. Let's see. Here's another one. And there was a, like this I know, because this was on a more recent quiz. I put a question very similar to this on the bonus of the last quiz. Although I think I put a -1 instead of a +1, but the idea would be the same. So now we have 3 terms in the denominator. So now it's definitely not going to work to do that trick that we were using last time, where you kind of multiply and divide by something where you change the sign in the middle. Because now we have 3 terms, right? If you multiply and divide by something like sin x plus cosine x minus 1 over sin x plus cosine x minus 1, it's not going to work out as the difference of squares. It's going to multiply out into, like, well, at first you can use the difference of squares, but then you're going to have a sin x plus cosine x squared, which is going to multiply out into its old thing. So yeah, multiplying and dividing here won't actually do it. But we can hit it with Weierstrass.
There are 2 dx's in there. Is that intentional?
No, that is not intentional. One of those should be okay, so we have that. And again, I would, by Weierstrass. Our dx is going to be 2 over 1 plus t squared dt. Our sine x is going to be 2t over 1 plus t squared. Our cosine x is going to be 1 minus t squared over 1 plus t squared. And eventually, if you use these often enough, you'll just end up memorizing them. And then I just actually plug these in. So it's the sine x plus the cosine x. This becomes 2 over 1 plus t squared. I'm going to multiply this out. The numerator is going to be a 2. The denominator is going to be a 2t plus a 1 minus t squared plus a 1 plus t squared. The t squares are going to die. And so now I would get something like a 2 over 2t plus 2, which is the same as, say, 1 over t plus 1. So simplify, that all simplifies into that, which just means it's that. Which is that. So that one, the algebra wasn't so bad, even though it looked crazier than the previous example because there were 3 terms. This one just so happens that it was a lot nicer because all the denominators were the same, the 1 plus t squared, and those guys got cleared right away. So that's what that looked like. So how are we feeling about Weierstrass? I mean, Weierstrass really just leads with an initial extra part, but after that, you kind of just do based on previous techniques. Are we feeling okay with so far? I don't know. Let's do another example. So here I have a double angle, and yes, yes, we could multiply by 1 minus cosine 2x over 1 minus cosine 2x. And this would be recommended here. We're going to talk about that in the next section. But let's use the hint. So here, the hint is basically like just modifying the Weierstrass substitution. So instead of a tangent of x over 2, we're just going to use tangent of x. And that's because our initial angle is doubled. So double the angle in the Weierstrass. Now I'm going to derive what the new formulas would be here just so you can see it, but they're actually going to be super familiar. So here, if my t equals tan x, this is a part of the answer. Let's actually derive it. Set t equals tan x. And then x would be tan inverse of t. This means your dx would just be 1 over 1 plus t squared. So this means you have this triangle where your x is here, and we have t over 1. This is 1 plus t squared radical, which means that your cosine of x equals adjacent over hypotenuse, and your sine of x equals opposite over hypotenuse. And so your cosine of 2x would equal 2 cosine squared x minus sine squared x. So it's 1 minus t squared over 1 plus t squared. It looks actually the same. There's just not a factor of 2 here because the factor of 2 is taken care of by the first part. You can actually see what is actually happening here. You could actually do a u sub u equals 2x, and you'll have a half factors out, and that will be what the half that gets canceled off of the numerator of the dx. But let's actually just run with this hint. Yeah, and so our integral would become, it's 1 over 1 plus cosine to beta. So it's 1 over 1 plus 1 minus t squared over 1 plus t squared times 1 over 1 plus t squared. So notice this guy kind of looks like a Weierstrass substitution, but we did a substitution of 2x before that. So it still actually works out pretty nicely. This all just simplifies rather nicely. This is just the integral of a half. So this is just going to be t over 2. So this is going to be just tangent x.
I've got a question.
Yes.
Just the beginning integral, if you multiply by half over half, could you use the identity that turns that into cosine squared? And then it just gets secant squared, which is tangent.
If we multiply by a half over a half?
Yeah, because a half times 1 plus cos 2x is cosine squared.
Yes.
Okay.
If I take 1 plus cosine 2x over 2, this is equal to the same as cosine squared. So, which means 1 plus cosine 2x is 2 cosine squared x. This could be dx over 2 cosine squared x. Which is just 1/2 secant squared, which is tangent squared, which is tangent. Yeah, so there are easier ways to do this integral. I just wanted you to see it. We got exactly the same answer doing it this way. So yeah, for this one, there are better ways to do this than the Weierstrass. However, this example, example D, example C, example B, those I would use Weierstrass. For example A, I think it would be better to not use it, as well as for this last example. I would think it's better to not use it. But then, like I said, we'll talk about when to use which technique in the future. At this point, I just want you to get practice with techniques without just making every single problem super complicated, right? So I'll give you some easy problems, but it's very hard to find an easy problem where it wouldn't have been easier to use something other than Weierstrass. So I just gave you some problems and just say, yes, I know you can do this without it, but just do it using Weierstrass just to get some practice. This brings us, yes.
Sorry, I just have a quick question.
Mm-hmm.
How did you go from when you wrote the double angle formula for the cosine 2x? How did you get that it was equal to the 1 minus t squared 1 plus t squared?
In which thing? The green thing or the blue thing?
No, it's in the white when you're like deriving all the substitutions and stuff.
Okay, you're talking about here?
Yeah.
Well, if my t is tangent x, I think of that as t over 1, so that is t over 1, that's opposite over adjacent. So my cosine is adjacent over hypotenuse. So that's 1 over the radical of blah, blah, blah. My sine is the opposite over hypotenuse. And so my cosine 2x is just cosine squared minus sine squared. That's just the double angle formula for cosine. So if I square this and subtract the square of that, if I square this, I get 1 over 1 plus t squared. If I square this, I get t squared over 1 plus t squared. And I subtract them, so I get 1 minus t squared over 1 plus t squared.
Okay, that makes sense.
Yeah. There's a part of this guy that's missing. Okay, so this is the last example, the integral of secant. I don't know what I did. Okay, undo. Undo. Okay, so secant. So we saw the standard strategy here. And that was to take the secant and multiply and divide by secant x plus tangent x. Right? And then we kind of realized that when we multiplied out, we would get secant squared plus secant x, tangent x over secant x plus tangent x. And then somehow you recognize this as well. The numerator is now the derivative of the denominator, right? Which is very convenient and is very cool, but like, how would we have seen this? Right? Like that was what we needed to multiply and divide by, right? It's something that it comes out of the blue, right? And so most people wouldn't see it, like most Calc 2 students, like if I've never shown them the strategy how to integrate secant x, it's very rare that a student's going to come up with this method. You know what? If I multiply and divide by this thing, that'll work out. Like it's hard to see. Like even when I'm teaching it and I tell students that this is what I'm going to multiply it by, it's like, it still takes them a while to figure it out. I don't know if you guys remember how long you guys took to figure it out, but you guys were actually one of the quicker classes to figure that out. Like, oh, it's like, wow, the numerator is the denominator, right? Usually it takes a lot longer, and even you guys took a couple of minutes to even see it. So even after I told you the answer, it was very weird to see. It turns out now with the Weierstrass, you see something that's a rational trig function, you don't have to worry about these things, like what is this mysterious thing that I'm going to multiply and divide by that's going to get this thing to work out. Like you can directly transform the integral. You can make a substitution to transform it. So in that case, if I had like a secant and I applied Weierstrass, so t equals tangent x over 2. Then what's going to happen is I know my dx is going to become 2 over 1 plus t squared dt. I also know that my cosine x is going to be 1 minus t squared over 1 plus t squared, which in fact means my secant x is just 1 plus t squared over 1 minus t squared. And I just remembered that. Let me just put a note in here before I forget. Because if I don't put it now, I'm going to forget. So just let me do a pause here. A regular Weierstrass substitution would also work in the previous problem. But for this example, I'd recommend not using Weierstrass. We'll talk about choosing strategies later. And how you do it without Weierstrass, there are two options. You can do what's in the green or what's in the blue. Okay, let's go back to secant. So we have that secant is that, so I can just actually just plug this in. So this means my integral is, well, secant would be 1 plus t squared over 1 minus t squared times 2 over 1 plus t squared dt. This would cancel here. And this becomes just 2 over 1 minus t squared. Okay, take it away. How do I integrate this? 2 over 1 minus t squared. Pretend that was an integral that you got. How would you do it?
Is that just 2 times hyperbolic tan inverse?
Ah, yes. Which kind of cheating, but let's yes. 2 hyperbolic tan inverse. Right. Even I haven't memorized all those forms. You're a better man than I, but let's do it a more typical way. How would you do it otherwise? Any other ideas?
Otherwise, can you?
Impartial. Oh, sorry. I was gonna say impartial fraction.
Yeah. So the denominator does factor. So what would the parts look like?
If you do the cover-up method, would it be a half over
Mhm.
1 minus t minus?
So if I do the cover method, I would get 1, right?
Yeah, sorry.
And if I did it with the 1 plus t, what would I get? I would get 1 again, right? And you can see that if you cross multiply 1 plus t, 1 minus t, you would get the 1 plus 1 minus t, you get the 2t. So that actually does work out. So this is actually going to be ln yeah. So now you'd realize that this is ln of 1 minus tangent x over 2 plus ln of 1 plus tangent x over 2. And that would be the answer. That's the integral of secant, right? And I didn't have to come up with any mysterious multiplying and dividing thing. Now you might be concerned because you're like, I know what the integral of secant is, and it doesn't look like that. It turns out that these two things are equivalent, and I believe I actually asked you to actually work that out here. Does this match with our previous formula? Right, was the additional question I asked here. So here the question is this equivalent? Does anyone actually see how they would make that equivalent? So if I start with ln of 1 plus 1 minus, or I guess 1 plus or 1 minus, doesn't matter. 1 minus tangent x over 2 plus ln of 1 plus tangent x over 2. Can you get that to kind of look like the ln of secant x plus tan x? Do you see anything that could be done here? Yeah.
Could you use the log rule and write it as a multiplication.
As a product, right? So
Yeah,
it'll be 1
product.
minus tan times 1 plus tan. So I can combine these into 1 minus tan squared. Right? What can I do with that?
Secant squared of x over 2.
Is that true? What gives secant? Is it 1 minus tangent squared is secant?
It's negative. It's like 1 plus tan squared will be secant.
Right, so that's not going to work. I mean, maybe you want to switch to sines and cosines. That might make you see something nicer. This would look like, if I combine these, this would look like cosine squared x over 2 minus sine squared x over 2 all over cosine squared x over 2. Do you see anything at this point?
Can you switch it to be ln of cosine squared minus sine squared minus ln cosine squared?
Okay, how would that help though?
I don't think that's going to help. Never mind.
Other ideas?
Isn't it like, could you do, because I know like, actually, never mind.
Can't you just split them up into 2 fractions? Oh, wait. Yeah, no, wait, never mind.
Well, yeah, we'll get back the original, unless you see something else from the original version that's nicer to work with. What is cosine squared of x over 2 minus sine squared x over 2?
That's cosine of x.
That's just cosine of x in the top. Okay, so now things are starting to look nicer. We're getting a full angle instead of a half angle. Anything we can do at the bottom? I mean, we used this identity earlier. I mean, I would think doing something like writing this as 1 plus cosine over 2 might help. So this gives you something like 2 cosine x over 1 plus cosine x. And we could multiply by 1 minus cosine x over 1 minus cosine x.
So I would say figure out the culture that they're based on, talking to teachers at other schools as well, and then like where you're at, look around town, see if you can enjoy, taking a walk there. But it's 10 p.m.
Geez, I hope I got the signs right, because it looks like this guy's shaping up to have like a cosecant in it. Did I have my signs right? 1 minus t squared is canceled, blah, blah, blah. Combine this 1 plus t plus 1 minus t. That seems fine. I think I have all the signs right.
Looks like something we should work on for next time.
Okay, yeah, we're out of time. There's nothing else I wanted to do.
Can you spoil it? Are they equal?
Huh?
Will you
Yes,
just
they
spoil it
are
and say
equal.
they're
There is a
equal?
way to go from one to the other. I did it earlier, but I think I made a mistake somewhere where we were multiplying and dividing by something or whatever. Yeah, they're exactly equal. So it's not even like you have to get some weird constant out of the plus c or anything. No, this one is exactly equal to ln of secant x plus tangent x. So try to show that for next time. We'll pick up next time with that because we're out of time. So try to work this out for next time.
Professor?
Yep.
When I was doing the cover-up method, I got a half, but I'm not sure if that's the problem.
Oh, there is a sign problem. There should be a negative. Like right there. Why did you guys not catch that? Okay, do it again. So there should be a negative there. Because it was 1 minus t in the denominator. But I would do similar maneuvers to what I did here, but I think with that negative sign, it's going to work out nicer. Because there was a negative here. It's not going to be nicer. Maybe I can just do it quickly right now. So this I can think of as ln of, say, 1 plus tan x over 2 divided by 1 minus. And I would multiply and divide this by cosine x over 2 plus sine x over 2. So that would give you cosine x over 2 plus sine x over 2 all squared. The denominator would give me cosine squared x over 2 minus sine squared x over 2, which is just cosine of x. Okay, so that looks like it's going to work out now. Let's create some space here. So that's actually going to be cosine squared plus sine squared. That's going to be 1 plus 2 sine x over 2 cosine x over 2, which is just a double angle formula for sine. So that is 1 plus sine x over cosine x. And so now that's 1 over cosine, which is the secant, and the sine over cosine, which is the tangent. So yeah, exactly equal. Just had a sign error in our integration. Okay, so we're gonna wrap up there. That's it. That's the last integration technique we'll be doing. We'll talk about how to mix and match, how to choose techniques next time. But yeah, so quiz tomorrow is on Weierstrass as well as partial fractions. That's what we did on Monday. Okay. And I guess the bonus would be on more integration problems because it's going to be a while before, or maybe improper integrals would be the next newish thing. So if you have time, I don't know, or if you've done it before, you can review improper integrals. But for now, we are going to stop there. Okay. Thank you for your attention. Thank you for chiming in. We'll wrap up there. And yeah, that's it. Have a good night, everyone.
Thanks, Professor.
Take
Thanks,
care.
Are
All
there
right,
any
take
practice
care.
problems?
Come again?
Are there any practice problems for the quiz tomorrow? Or like something you want us to try for Monday?
No, you can actually just look at the problems in the textbook or something.
Okay.
Would be nice. Besides the homework, just look at the suggested problems in the textbook, which you guys should all have an e-version of the textbook. So in the syllabus, in all those problems that I asked you to practice, you can just read through some of those, make sure you kind of know what to do.
Okay.
That's
Thank
probably
you.
how I'd practice.
No problem.
Okay.
Nice night.
All right. Take care. Have a good night. See you in the next one.